Hello my friends, you already know how to use transactions in Postgres. You create applications that execute updates, deletes, inserts and other types of SQL statements over your database. And Postgres can execute those transactions and queries in parallel over a consistent view of data. How? It has its own MVCC engine, where MVCC stands for Multi-Version Concurrency Control. And today I want us to take a look at the backstage of MVCC in Postgres. So the flow is gonna be as follows. First, we will start with some hidden columns that are not visible to you by default. And then you will see how Postgres MVCC engine uses those columns to track various versions of your rows. And finally, we will talk about garbage collection in Postgres, because all of those old versions of the rows that are generated by your applications have to be garbage collected. So let's not waste a minute and do a deep dive. Alright, let's start with the hidden columns, my friend. I'm already connected to my instance of Postgres. Let's check its version. It's Postgres 16.1. Next, I want to create a sample table for our experiments. How about this table? I create table account, and it will have two columns, the ID of the integer type and the balance of the money type. The table is ready, but it's empty. Let's insert the first account into the database. Insert into account. Values, ID is going to be 1, and let's put down $500. Ready. If we want to get all the rows with all the columns from our table, we just need to execute select star from account, okay? And this is what we are getting, no any surprises. But interestingly, when you execute select star over your table, you are getting all the columns of your rows, but hidden ones. There are some hidden columns that are not visible to you by default. But every row in Postgres has a special header, and that header stores various fields that are used by the database engine internally. And guess what? If you know the names of those fields, you can get them back using the select statement. How about we do this right now? I know a few names of the hidden columns, and today I'm interested in the following three: ctid, xmin, xmax. And I want to keep getting back my visible columns. That's why I'm using the star here from account table. Nice. The last two columns, you already know them. Those columns we defined in our table definition, ID and the balance. The first three are hidden. They are from the header of this row. ctid, this is a unique row identifier. The first part is a page number 0 and then the ID of this row within the page. This ID is not fixed. It can change over time. The next column, xmin, it stores an ID of the transaction that created this version of the row. And that transaction had the number 755. It's generated by Postgres internally. Xmax is set to 0. It means that this version of the row is visible. It will be visible to all of our application requests when you execute them, like this one, okay, from account. This value is non-zero. It means that either this version of the row was deleted or there was an attempt to delete this version of the row. Okay, but we will talk about this later. Now let's see what happens when you insert extra rows in the same table. Insert into account values, and we'll insert two more values. The second account with the balance of $600 and the third one with the balance of $700. Excellent. Now let's get all the data back, including the hidden columns. This is our first account, and this is our second and the third. Take a look at the xman column for the second and the third. It's the same. Why? Because those accounts were generated by the same transaction. How? I use this multi-value inserts to add two rows to my table. That's why the xmin is the same. And now we've got the $1 million question, my friend. Why would Postgres need those hidden columns? One of the reasons is its MVCC engine. Postgres can store multiple versions of the same row at a time, and then it will use those hidden columns to control the visibility of the versions across your running transactions and requests. Right? Now let's see how it works in practice. Let's begin a new transaction using the begin statement. And next I want to get the value for the first account. We already know it. It's $500, and that's the ID of the transaction that created that row. Now I want to update this table. Update account, set balance plus $100, where ID is equal to 1. Wonderful, it was updated. And if you get the value back right now, you will see the following. The balance is equal to $600, and that's the X-min value for this version of the row is set to 757. That's the ID of my current transaction. How can you see that transaction? You need to execute the following request: txid current if assigned, and that's the ID of my transaction, all right? Next, what happened to the previous version of the row when the balance was equal to 500? It's still there and it will be visible to other requests until my transaction is committed. Let's open another database session. I'm connecting to my Postgres, it runs in Docker. And now let me just copy and paste the same request. I want to select the value of the first balance. Take a look at this. This request still sees this value when the account was set to 500. It doesn't see the new value. And that's the previous version of the row. The X-min is 755, not 757. However, you can see that in that first version of the row, the X-max is already set to 757, and 757 is the ID of this transaction that is updating the row. So what happens when we commit our transaction? Let's execute the commit statement. The transaction is committed, and if you execute the same select right now from here, you will see the new balance, and you are dealing with the next version of the row that was created by this transaction. The X-min is set to 757. The next question, my friend, what happened to that previous version of the row that was just updated? It's still there, you just don't see it because when you execute your selects from new connections, here you see the latest value, but the previous value is still there. Now I will show you how to find it. We are going to use the pageinspect extension. Create extension, pageinspect, done. Now, how do I use this extension? I will make a call to the getRowPage function of the extension. I will ask to return all the values from the first page of the account table. And then I will beautify this a little bit. I will translate this raw page data into the page items. And from that, I'm interested in the following columns. Let's run it. The LP column is a pointer to a version of the row within the page. The next three columns are already familiar to you: the unique row identifier, X-min, and X-max. And the last column is the actual data that is stored in the row. Let's take a look at the first row. That was the very first record that you put into the account table. You remember, with the balance of $500. That was the ID of the transaction that created that version of the row. And then later, when we experimented with the MVCC, we updated the balance of that row by increasing it by $100. And that's the ID of the transaction that deleted the old version of the row. However, the same transaction created a new version of the row. Here it is, with the balance of 600. So effectively, what does it mean? When you do an update in Postgres, you are deleting a previous version of the record and you are creating a new one. The other two rows here were created by our multi-insert when we added two extra accounts to our table. And the X-min is the same because it was just a single transaction. Effectively, you can see that Postgres stores 4 rows internally. But when you get select stuff from account, you want to get all the rows, only those that are visible. You are not getting this row, you're getting only these 3 rows. The first one is already deleted. Also, in addition to this CTID, X-min, X-max fields of the header, there are some other fields in the header that are useful from the MVCC standpoint. What I'm going to do next, I want to create this stored procedure, heap page, that will be reading those various flags and fields from the header of every row, and it will be putting extra labels and marks that will be useful for our experiments. This stored procedure was borrowed from the Postgres internal book, wonderful book by Igor Rogov. So credits go to Igor. So let me copy this function and jump back to my terminal window. It's created. And now let me run the following request. I'm calling this stored procedure heap page and I'm asking to return the page 0 of the account table. And that's what we are getting back. What do we see? The state of all the rows is normal, nothing special. Then xmin value for all of the rows has got the special C flag. It stands for committed. It means that this version of the row was successfully committed by the transaction with the ID to the left. Okay. Next H is how many transactions away was this version of the row created. Like that was the very first record that we added to the database, and it was 8 transactions away. Xmax value also has got a special flag. For instance, here is we know that the first version of the row was deleted by the following transaction, and that transaction committed successfully. The A stands for aborted, but you can disregard this flag of Xmax values with 0 because it means that these versions of the rows are actual. They are not deleted, they are visible. HU, it stands for heap hot updated. When set to true, it means that the database needs to skip this version because it's no longer the latest. Instead, it needs to go to the next version of the row referenced by the CTID column. So it's 0.4 and we are jumping here, and this is the next version of our row. Hot only tuple, if it's set to true, it means that this version of the row, it's not referenced from any indexes. You don't need to update any indexes at all. Finally, let's talk about garbage collection, because that was the primary reason why I decided to create this custom stored procedure and show you its internals. Imagine this. I want to update every account in my table. I want to update account, set balance, current balance to 100. I'm just adding extra $100 to every account I have. It's updated. So when you do this select from account, you will see the new balance for every account. However, it also means that Postgres stores 3 extra versions of the rows internally. How do I know that? You also know how to check it. Let's make a call to this heap page function that uses the pageinspect extension. And here is down below, you can find those 3 latest versions of the rows for all those 3 accounts that the select star statement returns. But what do you see above? Those are the previous versions of the rows for the first, second, third account. Okay? Let's say that you decided to carry on and you want to debit every account with $100 one more time. And let's do it one more time. Now, if you make a call to this heap page function, take a look at this. Postgres will be returning these 3 last versions of the rows, but above we have so many old versions that are no longer needed, but they're still stored in the database. And now you might have this question, my friend: for how long is Postgres going to store all these old versions of the records? Because we understand that it cannot continue forever, especially if we are building write-intensive applications. The database can literally run out of space if it doesn't do anything with this old data. And good news is that Postgres has a built-in solution. It has its own garbage collector, known under the name of vacuum. So it operates in 2 modes. You can start vacuum manually, or you can rely on the auto vacuum procedure, which is the advised approach. The auto vacuum will start regularly, and then it will be checking and iterating through your database objects, including this account table, and it will be cleaning the old data. It will be making the space available for your future records. Today, we are not going to sit and wait while the auto vacuum does its job. Instead, we will run the vacuum manually. For that, just execute this vacuum command, and you can specify the table if necessary. So the vacuum has done its job. If you run the same method heap page, take a look at this. These last 3 rows are visible. They need to be saved and preserved. The other space can be reused. The important thing is that when you execute this vacuum procedure, it doesn't defragment your data, it doesn't return anything back to your operating system. However, Postgres certainly can reuse all this unused space for your future records. For example, let's do this. Let's update account table one more time and set the balance to 1000 for their first account. Done. And what you can see now is that Postgres reused this space in the middle of the page for the new version of the row. That was the previous version of the row. It's deleted. Xmax is set to 766, and that's the next version of the row. Now, at last, What if you want to defragment your space, and what if you just want to return the space to your operating system? You can run the full vacuum command. Let me show you what happens and how it works in practice. I am jumping back to this vacuum, and all I need to do is to add full in here. It's done because my table is small. And now when you take a look at the internals of the Postgres storage space, you will see that that's all we've got. We have 3 versions, and those 3 versions are those that you see when you run this select statement over your account table. This is how MVCC functions in Postgres. Job done, my friend. How do you like this, my friend? Hope you enjoyed looking into the MVCC backstage with me today. At least now you should have a much better understanding of how Postgres functions internally when it needs to execute your transactions and queries in parallel over a consistent view of data. And if you wish to reproduce all the steps on your end, in the description to this video you will find instructions that I followed today. So stay tuned for the new videos and keep mastering databases. Bye bye now.